All right. Good morning, everyone. Welcome to our last day of our school. Please come at 11:30. There will be a small thank you ceremony. Now we have Professor Joao Penedones from EPFL. So he's going to tell us about S-matrix Bootstrap.
Thank you. So, so we will continue with this lectures on S-matrix Bootstrap applications to gauge theories, to confining gauge theories. But now we will change. So the first two lectures were about scattering on this confining flux tube, so scattering of the massless phonons or Goldson bosons on the flux tube. So today we will discuss scattering of pions. Okay, so really a four-dimensional scattering amplitude. So, so we will take the, if you want, the cleanest setup. Well, there will be two choices. Today, I'll basically talk about finite NC, and I think I will not have time to describe the recent work about studying S-matrix Bootstrap directly in the limit of infinite NC that Gian and Leonardo Hastelli have been pursuing recently. Okay, so that's one thing, finite NC. It means this amplitude will be fully non-perturbative. It's not a small amplitude. Okay, so we will really treat it as a strongly interacting amplitude. And then we will take the chiral limit. Okay, so we will work really in the limit. First of all, we will study, let's say, NF equals 2. So there's just like up and down quark. We neglect all the others. And we take the limit where both quarks are massless. So the precise chiral limit, which is cleaner theoretical, so that the pion is massless, is the Goldson boson of spontaneous chiral symmetry breaking. Okay, so right, so we will have chiral spontaneous symmetry breaking of the, well, SU2 left times SU2 here, SU2 right, to the SU2 diagonal, which will be the SU2 of isospin. Okay, and then the pions, so spin, and then the pions will just be a triplet of this isospin. Okay, so that's for us will be the global symmetry. So it means the pion is massless particle, and it's a triplet of this global symmetry of SU2 global. Okay, so from the point of view of the S-matrix Bootstrap, that's the only thing you need to know, that it's a massless particle and that there is this global symmetry. Okay, so that's one thing. Then let's see here. It's the last day. I don't have a lot of time to improve. Okay. So then the other thing that we will use is the fact that it's a Goldson boson. So that tells us what should be the scattering amplitude at very low energies. Okay, so that is described by the chiral Lagrangian. Okay, so the effective field theory for pions is what's sometimes called the chiral Lagrangian. So I will be very brief here. This was like in some of the pre-reading material. So, so the basic idea is that you parameterize the pion field by a unitary matrix. That to say, so a unitary matrix in SU2. Okay, and the pion fields will be just for the right normalizations. So the Pauli matrix is sigma A pi A. So that's your triplet. And then the chiral Lagrangian, the rule of this effective field theory is that has to realize the original symmetry that was spontaneously broken. So U goes to L lager U and R. So this is the SU2 left, and this is the SU2 right. And so then you write all possible terms in a derivative expansion with usual rules of effective field theory. And so we will need just the first few. So the Lagrangian. So the first term, there's only a single term with two derivatives that you can write. So it's usually written like that. Okay, you can convince yourself that since U is a unitary matrix with two derivatives, this is basically the only thing, the only term you can write. And this is a nice term. So if you now replace U by this expression and expand in the pion fields, you will see that with this choice, you'll get a properly normalized kinetic term where you have del pi square, a half of del pi square for a massless particle. Okay, so this is the first term, and it already gives you the kinetic term and many interactions, right? Once you start expanding, you will have all kinds of pion vertices. So I mean, maybe I should. So from here, you will get del pi square, the kinetic term, but you will also get terms with two derivatives, something like that, right? Let's say maybe del pi square. So the leading interactions of this type. Okay. But we will need a bit more than that. So we will go to the next order. So this term is completely universal. There's this only constant, this f pi, which is the pion decay constant. But well, maybe I should be careful so you will see it here. Pi square once you do this expansion. Right? Each pi field carries a 1 over f pi. Okay. So at four derivative order in SU2, there's two possible terms you can write. So let me, I'm running out of space. I think they can still fit here. So one, there is a constant I will call L1. It's one of these Wilson coefficients. And basically it's the square of the first term. So trace of this all squared. You can write it like that. And then there's another term which is independent at four derivatives, which is a different contraction. So you take also two traces, del mu u, del mu dagger, and then you contract the indices with another trace, del mu. Okay, and of course, then there's more terms at six derivatives and so on. It goes on forever. Okay, so this will be important for us because as in the case of the flux tube, when we do the S matrix bootstrap, we impose one of the conditions we will impose is that it matches at low energies. The S matrix must match the predictions from this effective field theory at low energy. So you can just go ahead and compute, right? Now you can take this Lagrangian, expand, and just compute order by order. Say 3-level, you just use this interaction. You can compute the scattering amplitude of 4 pions, 2 to 2 scattering. Okay, so this will be labeled. Each pion is labeled by this flavor index, this triplet of SU2. And so you will have an amplitude, which here I will call T, A, B, C, D. And again, just by the global SU2 or SO3 symmetry, if you want, there will be a tensor structure like that. Exactly. This is exactly as before. And then there will be a function. So now this is a function of two Mandelstam invariants, right? Because now we have both the center of mass energy and the scattering angle in the center of mass are Lorentz invariants. So let me write it. Okay, this is a very bit of a funny way of writing it, but it's convenient because, as we will see, this is crossing symmetric in between the last two variables, but not the first. So that's why I put this bar just to separate the variables. And okay, there's two other terms which are of the same type, just by permutating the indices. Okay, just for completeness, let me write it. Okay, so that's just the structure that follows from global symmetry. Okay, so ST and U are the usual Mandelstam invariants. Okay, so let me not write them all, but of course P1. So this is the square of the center of mass energy, similar for TU, and then you have the condition that S plus T plus U is 0, because that's the sum of the external masses squared, and in this case, with scattering massless particles. Okay. I really need to eat better at breakfast. Okay. So now let me just tell you the prediction. So if you take this effective field theory and you compute two leading order, so the first term, the term that comes from the two derivatives in terms of this amplitude, A of SC and U, is very simple. It's just S over F pi squared. Okay. So that's the two derivative prediction. It's extremely simple, just that. But we will need the next one, because our goal is going to be put bounds on these four derivative Wilson coefficients. Okay? So then we need to go to next order. And so let me write well, what you get. So it's four derivative term. So it goes like S squared. So I will introduce here different parameters, because let me first write and I'll explain. So this is actually what you get from four derivatives. So these alpha and beta are the Wilson coefficients. Okay, so they are equivalent to this L1 and L2. But if I just give you the Lagrangian, that doesn't tell you immediately what is the scattering amplitude, because you have to do a computation in a given scheme. Okay, so then I will define the scheme by fixing the scattering amplitude. Okay, so instead of bounding things in the Lagrangian, which depend on the scheme, I will bound parameters in the scattering amplitude, which then are physical and everybody agrees on what they are. Okay? So this comment becomes more clear here, because basically what happens is that if you compute one loop diagrams using the two derivative action, you also get contributions here of this type. So with logs. And you have to choose a scale in the logs. So we choose F pi square, which is the natural scale for this problem. And so if you want, that's a choice of scheme. What you put here in the logs, if you change this scale, you will change these constants. Okay? That's just Okay, and then the next term would be order S cube. Okay. So this part, if you want, comes from one loop diagrams, or in fact, the way we actually computed it, or recomputed it, this has been computed a long time ago, it's fixed by unitarity. Okay? So you can use, right, you can use like that, and then you use the optical theorem to compute just the square of tree level to get these logs, okay? But let me not go into that. Okay, so I guess from just pure theoretical understanding, this is what we know about this amplitude. So now I'm going to move on to the S-matrix bootstrap. What can we say using the S-matrix bootstrap approach? Any question about this so far? Yes.
So this expression, does it come from the Lagrangian?
Yes.
From, okay, so I didn't understand this last comment that you fixed that by unitarity.
Well, or you can do either way. You can just do Feynman diagrams, the one loop diagrams will give you these logs, or you can impose that at this order, the only states that flow here when you do the imaginary part of the amplitude are 2 pion states. And since you already know the tree-level amplitudes from 2 pions to 2 pions, which is just this term, you can also compute this term using unitarity. But this is the equivalent.
And why are there no alphas there? Because you redefine.
No, the alphas and betas, so these correspond to these terms here. They are directly 4 derivatives. So at this order, they enter just at tree level. Right? So you will have tree-level diagrams with 4 derivatives that are proportional to L1 and 4 derivatives. They will give you immediately just these contact terms. Okay. Yes.
There is also
Sorry, but isn't that what I'm saying here? Chiral perturbation theory, just take this Lagrangian and compute perturbatively.
right.
Yeah, yeah, that's what I mean. You just expand, you'll get this effective field theory for pions and just compute order by order.
Then they were just meant to data to.
You can also do that. You can take data and then fit with the data. Yes. Any other question? Okay, so okay. Let me see here. Let's see then how to set up this numerical S-matrix bootstrap for this problem. Okay, so let me first, before going to details, let me just give you the logic of the algorithm. It's an algorithm in basically 4 steps. Okay, so the first step, we're gonna write ansatz. We're gonna write an ansatz that satisfies many of the properties exactly. Okay, so we're gonna write an ansatz that satisfies, well, Lorentz invariant will be, it's very simple because we just write a function of the Mandelstam invariance. So this will be automatic. Then it will also be crossing symmetric. It will also be automatic. That's also easy. Analyticity will also do it. So we will do a similar trick to what we did for the flux tube by mapping the plane minus the cut to the unit disk. And we will also manage to do the effective field theory constraints automatic. Okay, so in the first step, we take care of these 4 exactly. Then the second step, it's going to be about unitarity. So we impose unitarity on each partial wave. Okay, so I will explain how to do that. But this one, well, we can write down the equations, but we cannot solve them exactly. So this one is where we go to a computer. And then in the last step is like, once we already have the ansatz with some variables, the constraints coming from here, we just choose. Okay, so in this case, we will minimize one variable. We'll minimize, for example, beta at fixed alpha, for example. That's just one example. The crucial point is that it should be a linear variable in the amplitude. Okay, otherwise this method, the optimization method, becomes much more complicated. Okay, and so to first approximation, there's just 3 steps, but if one is careful, there is one more step, because when you write an ansatz, here in this ansatz, there will be a finite number of variables, okay, that parameterize the amplitude. It will be, okay, it will be, I will introduce this parameter n max, it will be of order n max square. So there will be a cutoff. And here, there will also be a cutoff, because we cannot impose unitarity for all spins. So we will impose only for spins from 0 up to some L max. So there will be also a cutoff in the constraints. Okay. So in fact, if you then want to get physical results, there's a 4th point, which is to extrapolate. Extrapolate, so the number of constraints to infinity and the number of variables to infinity. Okay. So that's basically the logic. So if you have any question about the logic, it's a good moment, because then I will explain in practice how do we implement each one of these steps to some level of detail. No questions? Yes. So this is an effective field theory, right? It's not a UV complete theory. You don't, I mean, this effective field theory does not make any reliable prediction for what is the scattering amount of pions at high energies. At high energy is much larger than f pi. So yeah, so this is all correct at low energies. But here, the question we're asking is there an amplitude that satisfies this principle up to all energies? Okay, so is there, if you want, a UV completion of the amplitude that has some value of alpha and beta in the low energy expansion, but then can be extended, satisfying all these principles to arbitrarily high energy? And that's not obvious. And in fact, we were going to show that no, not all values of alpha and beta can be completed to arbitrarily high energy. Yeah. No, if you just truncate, if you say my amplitude is that, instead of push plus dot dot, this is the full amplitude, then this doesn't obey unitarity. I mean, this grows. This immediately violates. Yeah. So it obeys unitarity at very small energies, but I'm going to impose unitarity to all energies. So that's how you get bounds on this alpha and beta. Right, it's growing. Right, the amplitude is growing, so definitely this is not the complete story. This will give you probabilities greater than 1.
If you know that the theory is going to break down at some high energy, what's the motivation to finding this, to making it unitary all the way up to high energy?
So, yeah, I'm not expressing myself. Let's see. So pions, we know a UV complete theory, right? QCD. Yeah. And pions emerge just as low energy excitations. Now, it is a well-defined question to scatter pions at any energy. There is an amplitude that describes that. We just don't know how to calculate. It's a strong coupling problem, right? And now the question is, what do we know about this amplitude that exists? It's not my invention, it exists. I can scatter pions at any energy. What do we know? Well, we know the low energy behavior because we can do effective field theory. Okay, and now you can ask, in effective field theory, these numbers, alpha and beta, are anything. They just parameterize our ignorance. Now, here we are saying, does anything go in this full scattering amplitude that exists at any energy? Can it have any alpha and beta when you expand at low energies? This is what we are trying to check. And we will find that no, not all values are possible. Does this make sense? More or less. Okay.
I mean, I guess, you can, at high energies, you can trust QCD. So I guess the question was like, if you scatter pions at high energies and you use QCD, do you get the same amplitude?
Okay, that's a good question. You're saying, since we know that the theory is asymptotically free in UV, can we use information about the UV theory to further constrain this S matrix of pions? But that's hard. So in fact, depends on the regime. If you do fixed angle high energy scattering, indeed you can use QCD because it really reduces to hard scattering of the partons of. But if you do, for example, high energy at low T, low scatter, like total cross section at high energy, is not described by a weakly coupled act. The total cross section of protons grows with energy, and we don't know how to compute it from first principles. And the same for pions. So that's an interesting thing. If we can input, for example, hard scattering at fixed angle, I don't know how to do it, but that's a good point. Could we improve, add to this list of constraints of this S matrix that it has to have the right hard scattering limit at high energies? Yes. I don't know how to do it, but it's a good point. Yes. Yeah, you can be anything. It's a way of saying it. In the end, the plot, there's only one bound, which is a minimum of beta for every function of alpha. So there's no maximum of it. So it's because I know already what is the shape of the formula. But yeah, morally, we're gonna test if a pair alpha and beta is allowed or not.
Just met out the boundary rather.
Yeah, exactly. Okay, well, that was important because it's the crucial point. So now let's see how to do this without too much detail. Well, crossing, I already said it. I can write it already here. So if you are careful about P1, P2, P3, P4, and as before, you permute the particles, you will see that crossing symmetry is simply the statement that this reduced amplitude A of STU is symmetric under the interchange of the last two variables, okay? And you can check that one is, so that's easy. So the non-trivial, the more non-trivial part is analyticity. So let me explain that now. So for analyticity, we're gonna take the following point of view. We're gonna first think that S, T, and U are 3 independent variables. And we're gonna demand, okay? So for analyticity, we're gonna say that S, T, and U are 3 independent variables, and then in each variable, we require the maximal analyticity, if you want, which is just that from 0, you have this cut from 0 to infinity because it's the production cut of massless particle. So this is, well, you see it already there, right? These logs, that's why I put log of minus s, log of minus t, so that the standard branch cut of the log puts the cut on this position, okay? So that's on each, okay, for S, T, and U, we'll have the same type of analytic domain. And then at the end, we will only consider the section of these functions of 3 variables given by the kinematic constraint S plus T plus U equals 0. Okay? So that's one way of, sometimes this is called Mandelstam analyticity. So then the trick is as before. So once you know that, we do the trick as before. We map this to the unit disk. So here you can choose some map similar to what we used last time. Well, it's slightly square root of minus s. I guess here from now on, I think here I'm setting f pi, okay, I think in the paper it shows 1/4 for some numerical advantage, but okay, it's not very important. F pi is set to 1/4 by a choice of units. And then in this, now this variable rho lives in the unit disk. This corresponds to s equals 0, and this corresponds to s equals infinity. Okay? So this map opens this cut to the boundary of the unit disk, right? So the top of the cut goes to this top and the bottom. Okay, so why is this trick good? Well, now we can write a nice ansatz that satisfies all the properties. So step number 1, let's write this ansatz. So okay. Well, the idea is the following. So since you have a function, should I write this? Well, let me write just this version. So I write a power series in rho, and then because of crossing symmetry, so rho s, rho t, and rho u should be the same. Okay, so this gives you functions of s times t, function of s times u, and so you're missing just a function of t times u. So this you just sum here some other coefficients symmetrized, rho t to the a, rho u to the b. Okay, so these are now the variables like before, like last week. So these are the variables, this and this. And as before, we have to put here some cutoff. So these indices A and B go up to some n max. Okay. So yeah, perhaps one thing you are puzzled, why don't I write rho s, rho t, rho u to 3 exponents, A, B, C, right? This would be the more general, right? Why not that? Okay, so you can do that, that's fine. And then But this is a redundant parameterization, right? Because in practice, you're trying to parameterize a function of two variables. There's only two independent variables because of this constraint. So that will make your numerics more unstable because you are over parameterizing the function. So this is a way to remove that redundancy. And it's also the way related with the, well, for the people that know it, the Mandelstam representation, where you write a function of three Mandelstam invariants just as products of sum of three terms, function of S and T, function of S and U, and function of T and U. Okay, okay, it's a bit of a technicality. Any question about this? So that solves the first three. Now we have to still satisfy the effective field theory. So clearly this will not satisfy the effective field theory because there's no logs, right? So that we just put by hand. Okay, so that we just add directly by hand. So so what we do, well, it's a bit of a long expression, but very simple logic. So let's see if this works. Ta-da! You had that. Okay, it looks a bit scary, but it's very simple. The point is that you don't want to write exactly what's up there, like S times log S, because if you write S square, then it will just grow to infinity inside your unit disk, and it will violate unitarity for sure. So what you want to do is to define some function. So let's say here this chi of S, which is bounded, okay, some polynomial in rows, so it's perfectly bounded inside this unit disk, and starts as S at low energies. Okay? Then instead of writing S's and logs of S, you write chi's and logs of chi, and that's it basically. Okay? And there's some constants you have to be careful to match exactly. And then on top of that, you have to impose that this part doesn't contribute up to order S square because this already matches order S square, okay? But that's just some linear constraints. So EFT just gives you a set of linear constraints on these variables. I call them CAB and DAB. Okay, so so step number one, that's it. Any question about step number one? It's not very important. What's important is that it's bounded inside the disk. So you shouldn't write polynomials in S. You should write polynomials in rho. And it's also important that it starts as S because rho has square roots of S. So if you just use rho, you will have square roots. And you want to postpone the square roots as much as possible. So here we postpone to S to the 5/2, so that the ansatz matches exactly effective field theory up to S square, and then it will have terms which are wrong. It will have terms that go like S to the 5/2, which is incompatible with effective field theory, but they are subleading to the terms we're trying to understand. So that's not very important for the numerics. You can improve it. You can put more constraints so that it's good up to the next order, up to S cubed. So that's a choice. It's not crucial. But up to this order, it's crucial. But if you have something like S to the 3/2, you will never be able to measure alpha and beta properly because they are smaller than that. Okay. Any other question? Is more. Not much, I think, if you look at it carefully. It's like, right, you just replace TU by chi's. It's almost the same. There is this term here. This term here is basically because here there is no, maybe I could have put it here, f pi. That one is perturbation theory. So that's the low energy behavior of the amplitude up to order s squared. Yeah, so this amplitude is valid to all energies, but at low energies has exactly the same expansion. This is what I'm imposing. Is it okay? Okay, so now we have an amplitude. We did step, okay, the steps are behind, but step number one. Step number two is unitarity. So here, yeah, let me just write this equation. So here, what one does is to expand in partial waves. So, okay, some normalization is not very important. So partial waves, so what does it mean physically? You go to a basis of two particle states, which are eigenbases of total angular momentum and total isospin. Okay? So when you send two pions, you can have three isospin channels, 0, 1, 2. And okay, that takes care of the indices again as projectors, like last time, like for the flux tube. And then you have a sum over actual spin, 0 to infinity. Okay, there's 2L plus 1 usually here. The Legendre polynomials, PL of the scattering angle, U minus T over U plus T. And then the actual coefficient, which I will already write in the notation I like, so this will be the partial wave of angular momentum L and isospin I as a function of the center of mass energy. Okay, so you see, this is just, once you know the formula, so you know T in terms of A, you can just go here and expand in this basis of projectors and Legendre polynomials, and these functions will be, so these functions from this formula will be linear in the variables CAB and DAB. Okay, so this you do in a computer, but it's a simple operation of you just integrate the amplitude against the Legendre polynomials. They are orthogonal, so you pick up this S. And once you have that, then unitarity is just a statement that each one of these partial waves is like a one-dimensional partial wave, has to be less or equal to 1, okay, for all S greater than 0 and for all L. And so here is where you put your cutoff, L max. And for all I. Okay. In fact, it's okay. If isospin is even, then spin is also even because of both symmetry. If isospin is odd, then spin is also odd. So okay. That's just a detail at this level. Okay, so unitarity, that's how we impose it. Any question about this? Yes. That would be just equal to 1. In terms, I think you're thinking, so usually you will see S as 1 plus I, well, FL of S or something like that. And then this one satisfies the equation you're saying that the imaginary part is more. But so I'm already putting it in this one. Okay, so that's it. Now point number 3 is to go to STPB, and you have linear constraints. So these are quadratic constraints because S is linear. You make a grid in S L, so the greediness we can make very dense, so that's not the limitation. But L, we really have to truncate up to some L max. And so that requires more careful extrapolation. So I guess I can show you here the results. So let me plot it like this. So as I said, for every value of alpha, we minimize beta. So if we maximize, there is no maximum. So that's why I'm doing that. And the bound is something like that. So how should I do this? Let me maybe use the same color. It's not, yeah, it's something like this. And then as you increase n max, you can come a bit later. Okay, so this is n max increasing. So here, I think in the end here we got to this red one. I think it was n max equals 24, which corresponds and L max here. I think we had 90, up to 90 spins. And if you want some order of magnitude, let's see. Yeah, something like that would be 10 to the minus 2 and something like that. So, yeah, 10 to the minus 2, something like that. That's the scale. So actually the scale of variation. So then if you continue this for bigger alpha and beta, you see that the bound becomes very trivial. It just becomes asymptotes to the curve. Here it asymptotes to a curve which is alpha plus 2 beta greater than 0. And here it just asymptotes to the curve beta positive. Okay, very quickly it asymptotes to that with, well, okay, with some small logarithmic corrections, but okay, let's not go too much into that. But you might ask, is this the natural scale? So in a way, if you do what's sometimes called naive dimensional analysis, since alpha and beta appear at the same order of these one loop diagrams, so you expect alpha and beta to be of order 1 over 4 pi square, and that's indeed the scale at which you see a non-trivial bound. Okay, so this, let me just make it clear, this is the allowed region, and here it's forbidden though. So what other comments? How am I doing on time? So I started at 30 or 30 something, so I have about 20 minutes. Okay, any question about, yes? You go to higher orders. So if you go to high orders in perturbation theory, you will have more Wilson coefficients. And so you can ask in a higher dimensional space of these Wilson coefficients, what are the bounds? That's an interesting question. We didn't do it. It's a good project. Yes. Comparison with experiment. Very good. So if you fit alpha and beta to experiment, so I mean, there's lots of subtleties because in the experiment pions are massive, and as the spin is not exact and all that. But I think several different ways to estimate tell you more or less that QCD is somewhere here, somewhere in this region. I guess that's an estimate of the error bars. You can see in our paper there's some many different ways of estimating that, but it's something like that. So it's close to the boundary, and in this region, it has the right order of magnitude. Yeah. Sorry. The dual. Good. That's a very good comment. So it would be great if we had a dual method, because if you see the plot in our paper, we show you several curves and they are still a bit moving. So we don't know exactly where the optimal bound is stopping, because this extrapolation step is difficult here. So this point at which we stopped had already like 500 variables, order 500 variables, so it was already tough. So now I think we know some better tricks. So for example, adding logs at next order probably will help convergence. So I think Kellyan is the specialist that has been pushing that in some simpler model. But it would be great to have a dual formulation. But in higher dimensions, the situation for dual is still very preliminary. So there's basically two proposals in the literature. One by Amit Sever and Andrea Guerrieri. And this one is extremely nice because it doesn't even assume this maximal analyticity, only uses the fixed T dispersion relation in the S plane. However, it has a drawback, is that it only works for massive particles. Okay, so it just doesn't, yeah, there's no, we don't know how to extend it to massless particles. It's very tightly bound to this, to have a mass cap. Then there's another approach proposed by Martin Kruczynski and Yifei He. And that approach in principle can work for massless particles. So basically that approach starts directly from the Mandelstam representation, where they parameterize the double discontinuity and then they act with functionals, a bit like I was explaining on this double discontinuity of the amplitude. So I think it's worth pursuing, but so far what has been done with that is just like single, also massive, and not for this problem with SU2 symmetry. So it's unclear how it will work, but yeah, that's a good open question for the future. So maybe I should comment on these asymptotic bounds, which these bounds are very old. So these bounds were derived already in '85 by Pham and Trong, and then they were rediscovered in this famous paper by Sergey, Adams, Nima, Nicolis, and Ricardo Rattazzi, where they discuss this connection between causality and bounds on the effective field theory. And so the exact bounds, so these bounds of that here appear as asymptotes can be derived exactly if you forget about the loops. If you forget about the cuts, you just assume that the amplitude is analytic up to say the next particle that will contribute, say the rho meson or something, then you can derive them exactly. Okay, so here, if you take into account the loops, you will see that these bounds are not exact, but you can derive them asymptotically, and there is some small logarithmic running on top of that. Okay, so that's another comment. Okay, so but as before, now if you have this bound, you don't have just the bound, you have the full amplitude, right? Because when you maximize here, you get the full set of variables, C's and D's, and you can plot the amplitude and see what is the physics in these amplitudes. So let me try to tell you what we see. And then you can compare with the data. Yes, I think you can create an amplitude with arbitrarily large alpha or beta in that direction just by putting a very light resonance. So if you put a very light, you can write an amplitude, say, where you exchange a very light resonance. Well, a bit like Sergey was doing. Add a particle to the effective field theory, very light, but okay, you in the amplitude you give it some small imaginary part because it's not a stable particle. goes below this cut. And then you ask, how does that, when you integrate it out, how does that contribute to alpha and beta? And you see you can make it very large. So the fact that we cannot put an upper bound is related to this question that we don't know how to impose. We know that the most important resonance here, the first one, is the rho meson. And that appears much higher, right? It appears several, I don't know, it's a factor of what, 6 or 7 bigger than f pi. Yeah, so it's higher. But we don't impose that constraint. And it's hard to impose that constraint because that would be like an absence of zeros in some neighborhood of the origin. So that's a difficult constraint to impose on an analytic function. If you want to say that it cannot have any zero in some region, it's not a linear constraint on these coefficients or anything. Okay? But that would be an interesting improvement if we could do that. Okay, so what's the best way? Maybe I'll mark here. So there's two, it's basically like in the other case, there's two different regimes. Maybe I'll mark them in colors. So let's say this is the blue regime here on this side of the bound. Let's say take this region as exemplative. And this yellow region here on this side of the bound. So these two regions have very different physics, very different types of resonances. Essentially, the slogan is that on this side, you have resonances of even spin, and on this side, you have resonance of odd spin. So if you want to see the rho meson, you have to be here. And here, you will not see the rho meson, and you will see just some other resonances in spin 0 and 2. So neither side matches very well the, should I plot this? Yeah, so let me show you the success, and I'll tell you what doesn't work testing words. So suppose you take the rho meson channel, so the L = 1 isospin 1 channel, okay, and you plot the phase shift. Okay, I didn't define it, but it's like last time. The phase shift is just you take this and you write it as e to the 2 pi, e to the 2I delta Li. Okay, so there's a phase shift for every partial wave. So this is, if you want, definition of the phase shift. So if you plot this for the L = 1, I = 1, as a function of S in units of f pi. Okay, so starting from 0 up to pi over 2. This is delta 1, 1. So what do you see from the experimental data? You see a very clear resonance. Okay, jumps to pi. Okay, here around the, I guess here in units of f pi is like 60. Well, because it's squared. It's the mass of the rho squared in units of f pi. Okay, so here to do this comparison, of course, we take the phase shift of the real pions, and there it starts from 4m pi squared. So we subtract that to compare with massless pions. Okay, there's some tricks you have to do to compare the real world that has massive pions with this setup that has massless pions. Okay. And then if you take the extremal amplitudes in that region, you get very close curves. Okay, of course, as you vary along the boundary, they will change slightly. So there's several curves you can plot. Some are closer than the others, something like that. Okay, so it matches at least very well qualitatively the experimental data. There's a rho meson with similar mass and similar width. However, if you take that yellow region and you compare the other phase shifts, it's pretty bad. Okay, so the isospin 0 and spin 0 is pretty bad. So I can show you on the other side. So here, let me show you on the other side something else that works. So for example, well, even this one works more or less. Just for simplicity, L equals 0, I equals 0, so the scalar channel. So here you also have okay, there's some data. Also, you go up here, something like that. There's lots of data here, and then like about 100. I think, but this I think has to do with the KK bar threshold opening. Something else happens here. Okay. So that part we for sure don't describe. And let me plot then in blue. So if I take that blue part, I do get something that grows like that. And okay, there's many curves depending exactly where you are that give you something not very different from this. Okay, but as I said, if I take that yellow part and I plot this phase shift, I just get something like this, okay, completely off. And if I take that blue extremal amplitude and I plot here on this channel, I also just get basically no phase anywhere. Okay, so QCD is neither on one extreme or neither on the other. So somehow it's probably where that rectangle is in the middle. It's not exactly at the boundary. So from this analysis kind of reinforces that QCD is probably somewhere here that has some resonance that we see here at this extreme and at that extreme. So one interesting.
Why can't you do this? Like, can you paint the red square in the middle now under the segment?
Here. Yeah. Here I can. Along the boundary I can do everything, but here it's even worse. If you go along the boundary, here you have neither resonances. So it's not here like this one disappears and this one disappears. So at this point, it also doesn't match QCD. It has to be, QCD has to be inside. It's not along the boundary. That's what I'm trying to say.
Can you play around with that?
So in this method, you don't know the amplitudes in the middle, right? You only get amplitudes once you get an extremal solution. In the middle, these coefficients can be anything. You don't know. Well, you could do it differently. You could say, I want alpha and beta to be some value. That you could do. Alpha and beta to be some value, fix it here, and then you maximize or minimize something else unrelated. And that you will get an amplitude that lives there. But still, there's many amplitudes that live there. So which one, how to choose it, that's an open question. That's an art.
I guess it would take a lot of time to explore the square.
No, it takes some motivation. No, I think it would be doable. It's just that, yeah, Andrea here has many interesting projects to do. So I guess that's the limitation. But maybe that will be helpful that I'm teaching here. You know, and more people can help. No, I think there's a lot of things to explore here. So, for example, an obvious thing is to impose the row meson, right? Because we know very well where it is. We can just say that add a constraint that the amplitude has to have a 0 at that point, okay, on the complex plane. And that's a trivial constraint because having a 0, just a equals 0 for that value is a linear constraint. So you can just see how the bound changes if you impose the row meson. So we didn't do that. It's an interesting problem to do. So here everything is based on massless pion, but we also actually before this work we did an analysis of massive pion. Setup is similar, but in that case you don't have an effective field theory to match, or it's a bit less clean. You can do still effective field theory, but then is not exactly the expansion around s equals 0, right? Because now you have a mass, so you start from s equals 4m squared. So that's a less clean separation between different orders in effective field theory. But you can just do it, use less effective field theory. And in that context, what we did was to parameterize more the amplitude by what's called Adler zeros. Okay, so the fact that in the chiral limit the amplitude is soft, okay, starts as S, so it vanishes at 0 energies, implies that once you go to the massive case, there must be a 0. It's not exactly at 4m squared, but there is a 0 between 0 and 4m squared. And exactly the position of this 0 is another way to parameterize the amplitude. So there's an interesting game that we played in the case where the pions were massive. And in that case, it's easier to compare with experiment, yes. So, but that, you see, there you don't ask, in that case, we didn't ask questions about alpha and beta, precisely because the effective field theory connection to the amplitude is less clean. We asked questions about the space of these Adler zeros, and you can see we have some lakes and some peninsulas and some capes. I mean, okay. But I don't have time to explain all of that, but there is another interesting story in terms of those observables. Okay. More questions? Okay, so let me just then comment on things that other things that would be interesting to do. Well, so one of them is what Jan and Leonardo Castelli are doing. So that would be to take NC equals infinity. Okay, so that you have to kind of change the methods entirely, but it's very interesting. In some sense, you get even more powerful methods because now in this limit, the amplitude, this amplitude is very small, right? So it's of order 1 over NC and times some meromorphic function. So you don't have to parameterize any cuts. It's just a meromorphic function, just with poles, like the Veneziano amplitude, if you want, as an example. And so there's an entire new set of methods that becomes available. And there's also all kinds of selection rules that follow from the planar limit that you can use to further constrain these amplitudes. So maybe you can invite one of them in the next edition of the school to tell you about that development, because I failed to cover it. Yeah. So that's a very interesting direction. Then another thing that would be interesting to do would be to extend this setup and couple the pions, not just to do 2-to-2 pion scattering, but study how the pions couple to probes of the theory. Okay, so for example, pions plus photons. So that's something that actually Jan and Leonardo did in this regime, but nobody did still in this non-perturbative setup. And this is very interesting because this gives you access to the chiral anomaly by coupling the way the pion couples to photons. Okay, so this is a way to access the chiral anomaly, and in that way, in principle, have access to NC, which in my setup, you see, the number of colors never appeared, right? So I don't know if I'm doing pion scattering in a SU NC theory. What is NC applies to all of them. Okay. So it would be good if there's a way to input that number. So this could be a way. Another similar way is if you scatter pions plus what's sometimes called dilatons. So the dilitons that Komagorski-Schwimmer used to prove the A theorem. And so we've done that already in the S-matrix bootstrap context, but not with pions, just with a single massive particle. And by combining the scattering of massive particles and dilitons, you can prove the A anomaly of the UV CFT of the theory. Okay? So again, this gives you another handle on NC because, well, the UV CFT, you know it's made of gluons and quarks, so you know what's the A anomaly. Okay, so that would be also an interesting, and we have all the technology to do it. Okay, for both of these problems, we have all the technology. We just have to sit down and shift enter in Mathematica to some extent. Dilaton scattering on flux tubes.
Yeah, you include dilatons.
Maybe. So the A anomaly comes from the 4 dilaton amplitude. It's a bit, so as I mentioned, one thing that one can do is to take the flux tube and scatter one particle. Now scattering 2 particles on the flux tube, I think it becomes harder. You will have too many Mandelstam invariants. 2D dilaton. No, but this, how does it make, because it's not a local quantum field theory. So how do I couple the dilaton to the flux tube in a 2D? And what would it measure?
Well, there is a theorem.
Right, so that's something we did into the quantum field theory. We can study the 2-point function of the stress tensor and get access to central charge. But then it's crucial that we have local operators. I don't know how to do that without local operators. The flux tube, I don't have local operator. I don't have a local stress tensor on the flux tube. Here, I'm probing, so this dilaton is coupling to the stress tensor of the 4D theory. So that's a local theory. I don't know how to couple just to the 2D theory. But maybe we can discuss, maybe there's some way of doing it. So what else? Another one, which I think this would be very, very interesting to connect with lots of experimental data, is nucleon scattering. Nucleon scattering. Okay, so proton in this approximation that isospin is exact, nucleon and proton are just a doublet of SU2 isospin with spin a half. So it's basically the same setup, but instead of being a space-time scalar isospin triplet, you do the same setup with an isospin doublet and spin a half in space-time. And this will be interesting because nucleon has a very weakly bound state, the deuteron. So you already know that there is a pole related to the deuteron. And there is some old works that suggest that the coupling of nucleon to the deuteron, right? So there will be like proton, neutron, deuteron. There is a cubic coupling that you can try to maximize. Okay, the residue of this pole you can try to maximize. So this will give, right, in the scattering amplitude of proton, neutron, this will give a pole, and you can try to maximize this pole, and that seems to be that the deuteron, there's some indirect ways to think that this coupling is actually maximum compared with analyticity to these principles of the S-matrix bootstrap. Okay, so, and of course it would be even better if you do the joint system, right, plus pion. So you now can scatter pions, nucleons. Pions appear as intermediate states between nucleons. So there is an entire nuclear physics setup that you could study in this work. Okay, that's what I wanted to tell you. Thank you very much.
Thank you very much. It was a very inspiring talk. Any further questions? Yes.
How difficult would it be to write as many bootstrap to observables like 3 to 3 scattering patterns?
3 to 3 in 4 dimensions. Very difficult. Yeah, that's yeah. Basically, the problem. Well, there's 2 problems. One is just you just get scared that you have too many Mandelstam invariants. So you have functions of too many variables, but that's okay. You just scared, but then you, okay, I can do it. The problem, the worst problem is analyticity, is that in 2 to 2, there is a conjecture, it's not proven from more basic QFT axioms, but there is a conjecture and it's compatible with all the perturbative calculations and so far, that if you scatter the lightest particle, the 2 to 2 amplitude of the lightest particle in a theory obeys Mandelstam analyticity, only has this cut that I'm saying here. But if you scatter not the lightest particle, or if you scatter more particles, because you can think that now here the reduced mass of these 2 particles is bigger, then you have much more complicated analytic structure, what's called anomalous thresholds. Okay? And we have a guess for what that is. So you can basically, to each one of the singularities, you can draw a Landau diagram. So a Landau diagram is a diagram where all the internal lines in a Feynman diagram are just propagating on shell, and that tells you where the singularities are. But the problem is that for a 3 to 3 amplitude, there's an infinite number of Landau diagrams. So like the analytic structure really becomes, I think there is no hope of really parametrizing all possible singularities and doing an ansatz of this type. The only hope is that at some point there might be a clever way of saying all the anomalous thresholds are in this region, so I kind of don't care about what happens in this region and I only parameterize the amplitude outside, and somehow I can still get bounds. But so far we have not been able to do that, and the obstruction is that if you have an analytic function, if you don't bound it in all the boundary of the domain, you lose, because basically any little hole, the analytic function can do whatever it wants everywhere else. You need to bound it in all the boundary. So that's, we kind of, the missing link would be to find some bounds in some region of the complex plane that hides all these non-trivial singularities. If we could do that, then I think we could push this S-matrix bootstrap to higher number of particles. The exception being what I told you on Wednesday. If you have massless particles in 1+1, then you can do all this, because massless particles either travel to the left or to the right, and if you have 2 of them, they act like 1, so they are still like a massless particle. So this case one can work on. But this is basically the only case where we know how to deal with many particles.
Any further questions? If not, let's thank Joao again.